On October 15, 1970, at 11:50 a.m., a catastrophic collapse changed Australian engineering forever when a 112-metre long section of the Westgate Bridge fell 50 metres into the muddy banks of the Yarra River, killing 35 workers and injuring many more. In today's episode, part 3 of Westgate Beyond the Collapse, we step through the events of the disaster and try to understand what happened to bring the catastrophe about, as well as take a step further back and gain insights into events transpiring around the world with bridges of this type. The collapse was the deadliest bridge disaster in Australian history and a stark reminder of the risks inherent in pushing engineering boundaries without adequate safeguards. But how did this happen? How could one of the most advanced bridge projects of its time suffer such a devastating failure? But the thing is, this tragedy didn't just occur in isolation. It was part of a global series of failures in steel box girder bridge designs, prompting urgent reforms in engineering standards. Today, we'll explore the tragic timeline of the events leading to the collapse, analyse the decisions and errors highlighted in the Royal Commission report, and place the disaster in the broader context of international failures with box girder bridge design. The Westgate Bridge was an ambitious project, commissioned by the Lower Yarra Crossing Authority, operating on behalf of the State Government of Victoria. The structure, designed by Monsell and the British firm Freeman Fox and Partners, featured a cutting-edge design, a cable-stayed bridge with 5 continuous steel box girder spans, supported by post-tensioned, reinforced concrete viaducts on either approach to the bridge. At the time, steel box girder construction was considered state-of-the-art, offering significant weight savings, high torsional stiffness, and efficient use of materials. However, from the very beginning, the project faced significant challenges. Labour disputes delayed progress. The original steel contractor was replaced mid-project, as highlighted in the previous episode, and communications between stakeholders broke down repeatedly, even prior to the handover of the project's scope taking place. By mid-1970, the beginnings of the eastern and western steel spans was happening at ground level, and the concrete viaducts being just about completed. Progress with these steel spans, however, had put the works well behind the project program targets. Each span was to be assembled in halves on the ground, lifted into place, and joined at height. It was during this process that critical misalignments emerged, setting the stage for the impending disaster to come. The immediate issue following the erection of the segments spanning Piers 10 and 11 was similar to that which had occurred on the opposing side of the river, with the span between Piers 14 and 15. In the case of this current segment, a camber misalignment between the north and south halves meant that the two would not come together without major intervention. This misalignment, caused by fabrication and erection errors at ground level, led to significant stresses in the upper flange of the steel box girders when installed at height. To correct this, the project engineers opted to try and force the misalignments out using Kentledge, 10 very heavy concrete blocks, each weighing roughly 8 tonnes, to force the spans into their correct position. While this approach temporarily reduced the camber in the manner which they hoped, it had introduced excessive stresses in the already thin upper flange plate, resulting in localised buckling occurring, which made the problem even worse for those involved. This localised buckling highlighted a systematic issue in the design and erection of the trapezoidal steel box girders. Thin panels under compression, insufficient stiffening, and poor detailed connections made the structure highly susceptible to buckling in hindsight. As noted before, though, this wasn't the first time the severity of this misalignment was seen. Only this time, remediation actions just exacerbated the issue at hand. The resulting buckle was approximately 380mm deep, far beyond any acceptable limits. The buckle compromised the girder's ability to carry compressive forces, creating a critical point of weakness if unresolved before completion. Despite what should have been seen as a clear danger, senior engineers decided to attempt repairs on the damaged span at height. The plan involved removing bolts from a splice in the upper traverse flange to relieve stress, allowing the flange to relax and straighten back out. At 11:40 am, workers began removing bolts, starting at the central splice. By 11:50 am, approximately 20 bolts along this splice had been removed, leaving a large area unsupported. Almost immediately, the buckle worsened. Without the bolts in place, the load on the upper flange had redistributed unevenly, leading to a progressive buckling of the wider structure itself. The girder twisted under its own weight, and the span then collapsed below. In seconds, thousands of tons of steel plunged into the river below, crushing workers and equipment. Many who lost their lives that day were on their lunch break, sadly, inside huts located directly below Piers 10 and 11 and the span being built above. That evening, 35 families would not see a loved one return home again, and many other families would see their loved ones only again within hospitals getting urgent care. The massive weight of the steel span and its collapse released an enormous amount of energy, causing debris to scatter across the construction site on the western side of the river. Witnesses described hearing a deafening roar as the structure gave way, followed by an eerie silence. This image, taken by Udo Rockman, a 10-year-old in the middle of a school excursion nearby, showed the scene only seconds after the span had fallen below. The scale of the disaster and ensuing anger had those in power call for an in-depth investigation, and a Royal Commission was also undertaken. The resulting Royal Commission report, released in 1971, laid bare the cascade of errors that led to the bridge's collapse. It identified multiple points of accountability across both the design team and the construction team. Freeman Fox and Partners, the consulting engineers, bore significant responsibility for the failure. The Royal Commission report criticised their reliance on outdated design principles and their failure to anticipate the sensitivity of the box girders to buckling. The design itself lacked sufficient safety margins, and key components were under-detailed, leaving much room for error during construction. The contractor, World Services and Construction, was also heavily faulted. Their decision to lift half-width spans separately created asymmetrical loads, amplifying stresses within the structure. And I imagine, in and amongst the dealing of blame, John Holland would also have been implicated. The methods for addressing the buckle, i.e. removing the bolts from the splice, was deemed reckless and uninformed. Part of this would have been pressure placed on all constructors to advance the works against the well-delayed program, but also made worse by the major disconnect between the workforce on the ground and the design engineering team who were meant to be available to support and aid in difficult choices such as this. Many other means of erecting the bridge structure were possible and had been effectively implemented under other projects throughout the world. But the one selected for the Westgate's construction was driven largely by cost reductions and appeared to have never been trialled or tested anywhere else in the world. The Royal Commission highlighted deeper systematic problems. Communication between the design team, contractors, and site engineers was poorly managed. Critical decisions were made without adequate consultation or analysis, and there was no independent oversight to review the safety of erection methods. This lack of coordination was compounded by the pressures of the tight schedule and the cost constraints. In their pursuit of efficiency, the project's stakeholders overlooked fundamental principles of structural safety. As mentioned earlier, the Westgate collapse wasn't an isolated event. The fourth Danube Bridge in Vienna had collapsed in late 1969, fortunately though without fatalities. Earlier that same year of the Westgate disaster in 1970, the Milford Haven Bridge in Wales also failed during its construction using a cantilever method, resulting in the deaths of 4 workers and injuring 5 others. A year later, only months after the Westgate Bridge Royal Commission findings were released to the public, the Koblenz Bridge in Germany suffered a similar fate, its collapse killing 13. Even during the Westgate Bridge's redesigning and rebuilding Another bridge, this one, the Zuhlenroda Bridge in East Germany, killed 4, like Milford Haven, and injured a further 5. Although the Cold War and the East German authorities kept that particular failure hidden from Western ears for some time. These bridges share many similar design features with the Westgate Bridge, including the steel box girder and stiffened plate construction configuration. These disasters underscored the limitations of the existing design codes, which had not kept pace with the complexities of large-scale welded structures. The recurrence of collapses within Europe prompted the UK government to convene the Merison Committee in 1970. The committee's scope being to conduct an exhaustive review of box girder bridge designs and their erection processes. One of its key contributions was the introduction of the interim design and workmanship rules. These rules emphasised rigorous buckling analysis accounting for local and global effects, improved detailing of joints and splices to eliminate stress concentrations, enhanced standards for materials and welding to ensure structural resilience. The Merison report also advocated for the use of finite element analysis, FEA, a revolutionary tool at the time to model complex stress distributions within box girders. The committee's recommendations didn't just improve safety, they fundamentally transformed how engineers approached large steel structures. The report also called for independent design reviews and tighter oversight during construction, measures that would become standard practice in large-scale projects. The lessons of the Westgate Bridge and other collapses were hard-won, but invaluable, a watershed moment for professional engineering. It exposed the dangers of complacency and underscored the need for rigorous standards and collaboration. While the tragedy of the Westgate Bridge collapse sadly claimed 35 lives and left many others with lifelong scars physically and mentally, it also triggered a legacy of critical learnings and reforms. The lessons of the Royal Commission and the Merison Report continue to shape engineering practices worldwide, ensuring that such failures would remain rare, if ever, to occur again. The collapse of the Westgate Bridge marked a turning point in engineering history. It led to profound changes in design philosophy and construction practices within transport and other sectors alike. But the story of the Westgate Bridge doesn't end here, of course. The bridge needed to be finished, having had so much more than money invested in it. In Part 4, we'll explore the redesign and rebuilding of the Westgate Bridge, along with the extraordinary efforts put into the structure decades after its opening in 1978 to strengthen it for future generations to come. I'm Paul Michael Angus. Please join me again as we continue this journey through the history of this engineering icon, Westgate, beyond the collapse.